Alright, today we're going to talk about integrators and differentiators. That is 13.3. As I already mentioned previously, we can use an op-amp for a lot of different purposes. In this case, we're going to look at the integrator and differentiator. Here we got an op-amp as an integrator. We will notice we put a capacitor in the feedback circuit. Input, it's inverting. The input is at inverting. That means if my input is positive, my output will go negative. If my input is negative, my output will go positive. All right, here's a few formulas from previous work. The charge on a capacitor is equal to IC times T, and the charge on a capacitor is also equal to the capacitance times the capacitive voltage. If we set these two equations equal to one another for the charge, then we can say VC is equal to IC divided by C times T. All right, the following is also true. My input current is determined by my input resistance Rin and the input voltage. Because, why? This point is at virtual earth. That's why that current will be determined by Vin divided by Rin. And we'll notice that the input current and the capacitor, the current charging the capacitor IC, are always equal when the op-amp is not being saturated. There again, they show us that IC is equal to In, and that means, in this case, a very important thing to notice. What we're doing, we charge the capacitor with a constant current, because the current will be determined by the input voltage and the input resistance. That's why we're charging the capacitor in a straight line. Normally, the charging curve of a capacitor is not a straight line, but now you'll notice, due to the fact that the input current will be constant, the charging current is also going to be constant. If the input is positive, I will integrate negative. We look at the following circuit. When we apply input step, that means from 0 to a positive voltage, what will happen? My input current will be constant, and that will also cause the charging current to be constant, and you'll see the capacitor will basically go from 0 charging negatively. Up to what value? It will charge up to the maximum value, and the maximum value in this case will be determined by my supply on the op-amp. That means the output of the op-amp can never go higher than my supply voltage. The rate of change, the change in output voltage divided by the change in time, is equal to minus Vin divided by Rin times C. That delta stands for the change in output voltage and the change in time. Let's have a look at the example. Let's have a look at the example 13.10. They say determine the rate of change of the output voltage in response to input square wave, as shown for the ideal integrator in figure 13.35a. The output voltage is initially 0. The pulse width is equal to 100 microseconds. Now I just want to point out, there's a mistake in this question. The value they use for the pulse width is equal to 200 microseconds. All right. Now the easiest way is to change this to 200 microseconds instead of 100 microseconds. All right, I've already told you that the pulse width is 200 microseconds. That means the question is basically wrong. Let's have a look at the circuit diagram. We've got a square wave that goes from plus 2.5 to minus 2.5. Here's a circuit diagram. You can notice that's an integrator. Rin is equal to 10K, and my capacitor value is equal to 0.1 microfarad. All right, here is my input signal. I already mentioned the pulse width is equal to 200 microseconds. Now what actually will happen, if my input goes positive, I will integrate negative. When my input signal goes negative, I will integrate positive. That's what actually will happen. We will actually change the square wave to a triangular wave. All right, let's go and have a look at the calculations. They state the rate of change of output voltage during the time that the input is plus 2.5, the capacitor charging is delta V out over delta T is equal to minus V in divided by R in C1. We know why the minus sign is there, because it will go in the opposite direction. When my input goes positive, my output will go negative, all right? All right, I will quickly repeat that. All right, I will repeat this. Because the formula states delta V out of delta T is equal to minus V in divided by R in times C. The minus sign just indicates when my input signal goes positive, my output signal will go negative. When we work that out, 2.5 volts 10K divided by 0.01 microfarad, it will give me minus 25 kilovolts per second, and that will be minus 25 millivolts per microsecond. All right, because everything's in microseconds, we rather work in microseconds. All right. Now for the rate of change of the output during the time that the input is negative, the capacitor discharging is the same as during the charging, except it is positive. Now my input signal goes negative, my output will go positive, and that will give me plus 25 millivolts per microsecond. They say when the input is plus 2.5 volt, the output is negative going RAM. When the input is minus 2.5 volt, the output is a positive going RAM. And then we can say delta V out is equal to 25 millivolts per microsecond times 200 microseconds. That will give me 5 volts. That is for the integrator. The next thing we're going to look at the practical integrator. There's my practical integrator. We have a look at the circuit. We still got the capacitor in the feedback loop, but we normally put a fairly high resistance in parallel with the capacitor. The only purpose of that is to make sure that due to my error voltage, this capacitor don't start charging up. It will keep it at discharge. And here is also my compensating resistor. We know about the compensating resistor from previous work. There's my compensating resistor. That is a practical integrator. The previous one, we talked about basically an ideal integrator, but here's the practical integrator. Now we're going to look at the opamp differentiator. Now the only difference between the integrator and the differentiator, in the case of the differentiator, we got the capacitor on the input side and the resistor on my feedback circuit. All right. The same formula still apply. IC is equal to VC divided by T times C. But now the only thing that in this case, what I can tell you that IC is equal to I in. But now in the case of IC is not going to be a constant current, all right? Like in the case of the integrator, IC was a constant current. In the case of this, IC is not going to be a constant current. Right. Now, in this case, in the case of the integrator, we applied a step function. Now, in the case of this differentiator, you will notice the input is basically a ramp. Now, because the input is a ramp, it will cause this current to be constant, all right? That means when it's constant, I will have a fixed output voltage. That means the voltage will also stay at a certain level, at a constant level, because that current is now constant. But that's due to this ramp input. If you apply a step input, then that won't be a constant. Then it will normally go to the maximum value. Right, here they give us V out is equal to IR times RF. We know that, that will be true. And because IR and IC is going to be equal to one another, I can also say it's IC times RF. Then I can say V out is equal to minus VC divided by T times RF times C. That is for my differentiator, and that is equation 13.8. All right. All right, here we apply a triangular wave to the input. That means it goes from 0 to maximum and then to 0 again on this differentiator circuit. That means when my input goes positive, what will happen? My output will go negative. And because that current is now constant due to this ramp, I will have a constant output voltage. When my ramp goes negative, my input will go positive and will stay positive for that duration of time. That means we actually changed this triangular wave to a square wave with the differentiator. Let's have a look at this example, example 13.11. They say determine the output voltage for an ideal opamp differentiator in figure 13.4 for the triangular wave shown, wave input shown, all right? This you will notice go from minus 5 to plus 5. In the time duration is 5 microseconds. And then it will go from plus 5 to minus 5 also in another 5 microsecond time. Right, let's go and look at the solution here. They state starting at t is equal to 0, the input voltage is a positive going ramp from minus 5 volts to plus 5 volts. That means the change from minus 5 to plus 5, the change is equal to a change of 10 volts. Not 0, I didn't say minus 5 plus 5, that will be 0, but the difference in voltage, the change in voltage is a 10 volts. In what is the time? The time is 5 microseconds. Then it changes to a negative going ramp from plus 5 to minus 5, again a minus 10 volt change, also in 5 microseconds. The time constant, to calculate the time constant of a capacitor, that is equal to the resistance times my capacitance value, and that will give me 2,2 microseconds. That means 2,2 kilo ohms times 0,001 microfarad will give me 2,2 microseconds. Now they say determine the slope of rate of change. That is equal to Vc divided by T for the positive going ramp, and calculate the output voltage as follows. Vc divided by T is equal to 10 volts because the change is 10 volts and the time is equal to 5 microseconds. That will give me 2 volts per microsecond. And then we're going to use the time constant, and we can work out V out is equal to minus Vc divided by T times Rf times C. That is my time constant, and that will give me a value of minus 4.4 volts. And then likewise the slope for the negative going ramp, and when you work that out, that will give me plus 4.4 volts. All right, now we can notice if my input goes positive, my output will go negative to minus 4.4 volt. When my input signal goes negative, my output will go positive to plus 4.4 volt. There is the output voltage of this opamp differentiator with that input. Practical differentiator. All right, now we can ask a few questions. Why do we put an input resistance here? Remember, the op-amp always try to make this voltage difference equal to 0. That means that point will normally be at virtual earth. Right, there is my compensating resistor, but that will normally be at virtual earth. That means when I apply an input signal and this capacitor is completely discharged, it will actually act like a short circuit, and we want to limit the current. That's why we put this input resistance here. That will normally be quite a small resistance, not a large resistance, but that's why we put the input resistance there. And there's my feedback resistor. That is a practical differentiator. All right, 13.4, troubleshooting. Students normally like troubleshooting, and that is normally sometimes quite nice questions to ask because you test a lot of things. But why do students don't like troubleshooting? Because, actual fact, if you want to do troubleshooting, you should know the operation of the circuit, and you should know if I apply this input to the device, that should be the output I should get. But now, if you don't know the operation of the circuit, then you won't be able to do troubleshooting. All right, let's have a look at this few circuits here for troubleshooting. The first, and you must know, if you look at this first figure here, you must know what type of circuit is this. This circuit is normally called a comparator, because what it's going to do, it's going to compare this input signal with my reference. And the output should also be 180 degrees out of phase with this input. All right? Now what happens? It stays at a high level. That means there's something wrong with my op-amp itself. The next one, also a comparator, input signal. That means the output should look like what? It should look like a square wave, 180 degrees out of phase, and it will go to the maximum values. But now it won't. There's something wrong. Same here. Here output failed in the low state. That is comparators. And this one failed to the output in the high state. All right. All right. If we look at this circuit here, it's also basically comparator. What can we say here? We got output bounding, and we got hysteresis. That means you should know in this circuit I will have output bounding and I will have hysteresis. All right. That means the output bounding will limit the output to a certain value, and the hysteresis will help us if there's noise and things to eliminate that. Right, let's have a look at the A. Figure A, the effect of the open Zener. Now let's have a look. I apply a sine wave. You can see the input is here at my inverting input. That means it should be 180 degrees out of phase. If I go positive, the output should go negative. But now what happens? It goes to minus maximum. When the input goes negative with respect to my reference, then it go positive. Now, what does it indicate? That indicates there's no bounding. All right. If there's no bounding, one of the possible problems will be an open Zener diode. Let's have a look at the next one. Also again, input goes positive, output goes negative. Goes negative to what? To minus Vz. Because we go negative, that is 0. This is 0 and this is negative. That means this Zener is going to be reverse biased. When it's reverse bias, that's why it goes to minus Vz. When I go negative, the output will go positive. All right, positive to what value? Then you will notice it will only go to 0.7 volts. That means this Zener diode is now forward biased. It acts like a normal diode. That means what is the positive fault? That Zener is shorted. It acts like a short circuit. All right, this one here, number C. Okay, let's go and have a look what happens. You will notice here we don't have any reference. When my input goes positive, it will go negative, and will go negative to minus Vz, and we actually should set the 0.7 also there. But that means in this case, I don't have any reference. R2 is open, that's why it will stay at that value. The last one, my input goes positive. What happens? It will go to minus Vz, all right? And now we can see, what does it do? It actually compares that with what? With 0 volts, with my reference. Because now I don't have any hysteresis here, because R1 is open. That means I compare that signal with 0. That's why it will give me a nice square wave. It will compare the input with 0. That means I won't have an upper trigger point and a lower trigger point, because R1 is open. And then we can say it's basically like a 0 level detector. All right, thank you. That's all for 13.4 troubleshooting. I will repeat, if you want to do troubleshooting, you should know the operation of the circuit, and then you can basically do troubleshooting. And you should be able to name the circuit, to identify the circuit.